All right, so we're going to talk about improper integrals today. We're going to get improper today. I know that was a stupid joke, but I can't help myself. I'm just going to do some examples for you. So you need to read the book. That's important. You need to copy those definitions in your notes. And then I will do some examples for you because that's what I really enjoy doing. And so, you're kind of stuck with me doing those. Hopefully they help, though. That's the whole idea of them. So let's look at this first example here, and let's look at the improper integral. I want to find, like maybe I have the graph of some function like the natural log of x over x squared dx. And I want to know, is the area underneath that curve from 1 to infinity, is that finite, right? So let's see what we're going to do here. So the first thing you need to do, and I know this is going to be a total surprise. I'm going to be very picky about notation. So you may not keep that infinite sign. Now, maybe eventually in your mathematics career, right, you're going to come, especially if you're a math major someday, we won't be as strict maybe about the notation. But right now, our definite integral that we have worked with does not know what to do with that infinity, okay? When we did the fundamental theorem of calculus, those were real numbers from a to b and our limits of integration. So infinity is not a real number. Infinity is not a number at all. Infinity is this concept, right? So we need to make sure that we deal with, something that our integral can handle. So you must replace that infinity sign with some sort of variable. I'm just going to use what your book uses. Your book uses the letter b, so I'm fine with that. So we can do that. Let's just look at what we have here. Now, as b goes to infinity, right, now I can deal with that somehow. So what I might do first is I might actually work with, it kind of depends on how you want to do this. You just need to be very good with notation. So what I might do is do a little bit of side work with this integral right here and see what it is. And then I will come back and bring in my limit. Okay, so let's look at, I'm doing some side work. Notice I'm not putting an equal sign, right? Because these are not equal because I'm not bringing, I don't know what that was. I'm not bringing the limit down with me. So I'm not going to put an equal sign because in mathematics, if you put equals, it must be equal. And let's look at how we're going to evaluate this. Now, this is why we spent a lot of time in this chapter, right, talking about how to evaluate these integrals. So I look at natural log of x over x squared. I kind of want to do u substitution, but I don't think that's going to work. If I let u be natural log of x, its derivative is 1 over x, so I would have an extra x there, so that's not really going to work. I might be able to mess with it a little bit, but I think the easiest thing for me to do here is to do parts. So I'm going to look at u being, remember, if we have a natural log involved, a logarithm involved, and I do parts, then I need the natural log. Remember the Liade or whatever, however your book does that. This is how we pick u, right? In order, if we have a logarithm, then our u is that logarithm. So I do have a logarithm. So what is du? Du in this case is 1 over x dx. I just rewrote that 1 over x squared is x to the negative 2. So I could easily take its antiderivative, add 1 and divide by it. So that's x to the negative 1 over negative 1, so that's a negative x to the negative 1. All right, and so now this is a definite integral, right, because I have 1 to b. Do sunny voodoo, so uv, so it's a negative natural log of x all over x, right, because that's x to the negative 1. This is evaluated from 1 to b minus the integral. So u me minus the integral of v du, so a negative x to the negative 1 times 1 over x dx. Oh, don't do that. Come on. There we go. 1 over x. I'm sorry. There we go, dx. Okay, so what does that give us then? I'm going to put in my b and my 1, so I get a negative natural log of b over b minus the negative natural log of 1. Oh, that's nice, because natural log of 1 is going to be 0. This becomes plus, and then what is this stuff right here? Well, this is just x to the negative 2, right? Because this right here is x to the negative 1. So, I forgot my limit sign. My limits of integration there. Antiderivative of x to the negative 2 is a negative 1 over x, evaluated from 1 to b, right? That'd be x to the negative 1 over negative 1, which is the same thing as a negative 1 over x. All right, so let's see what we get here. Remember, all I'm doing right here is I'm evaluating this definite integral right here in the box, okay? Because I know I want to take its limit eventually, so I will get there eventually. So this is 0, so I get a negative natural log of b all over b minus, right? I'm going to have 1 over b minus 1 over 1, which is 1. Okay, be careful with your parentheses there. Don't just, you know, I've been doing math a long time. I'm a mathematician. I have a master's degree in mathematics, and I still don't assume that I know what's going to happen with my negatives because I mess that up easily, okay? All right, so this right here, right, is this. I have found what this, this pink box is right here, so now I'm ready to go. So let's rewrite everything just so that we know what we're doing. So we want the limit as b approaches infinity, right, of 1 to b, natural log of x all over x squared dx is going to be equal. So remember what a definite integral wants us to do. Well, sorry, we found that definite integral, right? So I have the limit as b approaches infinity of all of this stuff right here. So I get a negative natural log of b all over b minus 1 over b plus 1. Okay, so now you may have forgotten this, and maybe you even had a Calc 1 where you didn't do L'Hopital's, but we're going to do L'Hopital's. So remember what L'Hopital's says. L'Hopital's says that I can actually take this limit. So, well, let me slow down a little bit. What's happening to 1 as b goes to infinity? You guys, it's going to 1. It doesn't care, right? This guy doesn't care what b is doing. It's just going to go to 1 because it doesn't matter. What about 1 over b as b goes to infinity? That guy is going to 0, right? 1 over really, really big numbers or really, really small numbers, and we're going to 0. Think as b, if b is a million, I have 1/1,000,000th. That's very, very small, so that guy's going to 0. So what are we getting really now? I'm going to have the limit then as b goes to infinity of this negative natural log of b all over b, and then I have this plus 1 over here, right, that I'm still dealing with right there. So let's look at how we're going to deal with the natural log of b over b. So this is a L'Hopital's. Natural log of b as b goes to infinity, that guy right there is going to go to infinity. What's happening to this b as b goes to infinity? It is also going to infinity. So when you use L'Hopital's, you need to tell me. And here's how you're going to tell me. You're going to write infinity over infinity. That's going to tell you what indeterminate form you have. And then you're going to put a little LH to tell me you're doing L'Hopital's. Okay, so I'm going to do L'Hopital's. L'Hopital's, remember, tells me if I have an indeterminate form such as infinity over infinity or 0 over 0, I can do L'Hopital's. L'Hopital's tells me I can take the derivative of the top. What's the derivative of the natural log of b? It's just 1 over b, and divide it by the derivative of the bottom. I'm not taking the derivative of the quotient, right? That's not what L'Hopital's tells me. L'Hopital's tells me just if the top and the bottom are basically going to infinity at the same time or 0 at the same time, then their derivatives will also be going to that same limit. The ratio of their derivatives will be. And so what do we notice here? Well, what's happening to 1 over b as b goes to infinity? That's going to 0. What's happening to 1 as b goes to infinity? That's going to, oh, not 0. That's going to 1. So 0 over 1 is 0. So my final answer is 1. If you have no idea what I just did with that L'Hopital's, you have to go on, you got to let me know. You got to look up videos on L'Hopital's or La Hospitals. L'Hopital's. I don't actually, I think that's how you spell it. But L'Hopital is, you got to know it. I don't think there's an S. I don't know. All right, so that was pretty cool. That shows me that this improper integral, right? If I were to actually take, if I wanted to know what is the area underneath the graph of the natural log of x over x squared from 1 to infinity, it actually is a finite area, right? It gets close enough to that x-axis that the area is negligible between the x-axis and that and the function. I just think that's so cool. That's really neat. All right, let's do another one. All right, how about something like this? Whoa. Well, first of all, let's get rid of that. How about something like minus infinity to infinity of, I'm going to do x over x squared plus 1 squared dx. Okay, so there's an example in your book, and you need to look at that example. The example 1, part B. That is an important example to look at. That's going to be in any calculus book you get that involves tangent inverse. You need to look at that example and make sure you understand it. This one is quite similar to it. We have minus infinity to infinity, okay, and we're dealing with x over x squared plus 1 squared. So what we need to do when we're going from minus infinity to infinity is we need to break this up, and we need to break it up. You can pick any number between minus infinity and infinity, because this guy has to be continuous from, over that whole thing. And this is because the denominator never equals 0, right? This guy is continuous everywhere. Its domain is everything. So pick 0. That's usually the easiest thing to do, right? 0 is easy to plug into an integral. It's going to be easy to do. And now what I need to do is I need to replace these my infinities, because I don't know what to do with that. My definite integral has no idea what to do with. So apparently all of a sudden I can't write and talk. That's not usual for me. It doesn't know what to do with infinity. Sorry about my voice today. So you got to replace it. You got to replace the infinities. I know it's going to take some time to write. Get over it. I don't know what to tell you. Don't be lazy. Just write it. Okay, so I am going to take a little bit of a break right here, because I have the same integral, right, integrand in each of these. I have x over x squared plus 1 quantity squared. So I'm going to do a little bit of side work here. So my side work I'm just going to do in a different color, and I'm just going to find what is an antiderivative, right? Because the fundamental theorem tells me I just need an antiderivative of this guy. So how am I going to evaluate the integral of x over x squared plus 1 squared? Well, if possible, do use substitution, right? And I think use substitution is going to work. I don't think I know, but you know. All right, so what 1/2 then du will replace that x dx. So again, I'm just doing a little bit of side work here so that I don't have to do a u substitution with each one of these. And then remember, if I do a u substitution in a definite integral, I have to change my bounds, and I don't really want to deal with that. You could change your bounds, but I don't want to. So I'm not gonna. So what does this become? This becomes 1/2 the integral of this x dx is replaced with that 1/2 du. That's where that 1/2 comes from. I get 1 over u squared du. That's the same thing as 1/2 the integral of u to the negative 2 du. And then if I take that antiderivative, right, that's u to the negative 1 divided by negative 1. I could put a plus c if I want to, but I know this is going into a definite integral, so I'm not going to worry about it too much. But I get a negative 1 over 2 times u, but what is u in this case? It's x squared plus 1. Okay, so I've done my side work here. It's not really side work because of the way this is done. It's like underneath work in a different color, but this is, this is the side work. I want to see this work, but if I were like proving something to someone, I would be like, oh, look, obviously this is, oh, wow, I don't want that. This is the antiderivative. I'm brilliant. I didn't even need to do anything. So we get the limit as a approaches minus infinity of, what's my antiderivative? Negative 1 over 2 times x squared plus 1, right, evaluated from a to 0, plus the limit. Notice I'm being good with my notation, right? I'm not being lazy. I'm showing my steps. That's something you should do. Where you make mistakes is when you try and skip those steps, right? All right, so let's plug in. So this equals the limit. Again, I'm writing my limit sign as I'm going on. My limit sign never went away because I haven't taken the limit yet. If I put in 0, I get a negative 1/2, right? Minus, if I put in a negative 1 over 2 times a squared plus 1. Okay, and then plus the limit as b approaches infinity, now not minus infinity anymore, of a negative 1 over 2 times b squared plus 1 minus a negative 1 over 2, right? Oh, I think we're going to get 1. Oh, no, maybe we're going to get 0. I don't know. Let's see what happens. All right, so what's happening in this guy is a goes to minus infinity. Well, as you go to minus infinity, you're squaring it, so that becomes a positive infinity. Not that it really matters, but what's happening is the denominator is going to infinity, right? The top is staying to be just 1, so that's 0. Remember, 1 over a really, really big number is a really, really small number. So what happens here? And then what's happening to this negative 1/2 as a goes to infinity? Well, there's no a in it. It doesn't care. So we just get negative 1/2. What's happening over here as b goes to infinity? Same thing, the denominator is going to infinity. So we're going to 0. We're going to 0 from the left. Not that that really matters, but we're going to 0 from the negative side. Here we are actually going to 0 from the positive side because those added. And then here, what does this become? This becomes a plus 1/2. What happens to 1/2 as b goes to infinity? It just goes to 1/2. It doesn't care. It doesn't care what b is doing. And so what's my final answer here? 0. Okay. So does this integral converge? It does. It converges and it converges to 0. Okay. If for some reason, like if we hadn't had that squared right there, our antiderivative would have involved a natural log instead, and we would have had the natural log of x squared plus 1. And what's going to happen to that is that's going to infinity as like x goes to infinity, or if there was an a or a b in there. So that would have diverged in a case like that. All right, guys, I want to do one more example of where we have discontinuity, where it looks like everything's going to play nicely with each other, but it's not. Okay, so you need to check that, like on the test. When this is going to be a big test, there's a lot of sections on this test. This is the largest test you'll have. You have a lot of sections on this test, and it's going to be a lot of just evaluating integrals. That's going to be most of the test. So you need to make sure that you don't just go and, start doing a definite integral without really thinking about, are there places where I could have discontinuities, right? Is Sarah trying to trick me? Not trick you. I'm not trying to trick you, but am I trying to get you to think about more than just what is actually there? Okay, so let's look at an example, something maybe like, I just want to make sure I'm doing something different than what your book has. Yeah, so let's look at something like this. Let's go 0 to 3 of dx all over 1 minus x to the 2/3. Okay, so this one looks like we would just do a simple u substitution, right? I'm actually going to make sure this works no matter what. Let's do x minus 1. My fault. Sorry about that. So let's do x minus 1. It doesn't really matter, but I want to do it. Let's do x minus 1 instead. We have an issue here, right? It doesn't look like we have an issue because we're just going along our merry way and saying we're integrating from 0 to 3. No big deal. But now we have to think about discontinuities in the integrand. So if you actually look at the graph of this, right, you go through at 0, you're at 1, but then it kind of goes like this, and it actually has a vertical asymptote at 1. So you have to be careful, you guys. It actually looks something like this. So we have to be careful about how we're going to evaluate this integral. So if I'm asking you to integrate from 0 to 3, I'm asking you to take this area right here. And you might say, well, Sarah, obviously that area, choose a different color, is infinite. But you guys, that's the thing with infinity that gets you a little bit. What actually happens is we're going to see that this is actually a finite area, that this integral actually does converge. Because what happens is this guy grows close enough to that vertical asymptote that distance between the vertical asymptote and the function is negligible, and it actually approaches a limit. Okay, but to be able to do that, we have to understand that this actually has a discontinuity. So we're going to have to go from 0 to 1. I'm going to rewrite this as x minus 1 to the negative 2/3 dx plus from 1 to 3. You have to do this. Yeah, I have to see this. Mathematically speaking, you may not just plug in 3 and subtract 0 into the antiderivative. And now because we have a discontinuity at 1, we need to rewrite this. So this is going to be the limit as, let's just replace that 1 with a. So as we go from 0 to 1, a is going to approach 1 from the left, 0 to a, x minus 1 to the negative 2/3 dx plus the limit. Now as we go from 1 to 3, right, we're actually approaching 1 from the right, but I don't want to use a. Let's use let's use b. We could have used b on the first one. If you like b to represent the variable on the top of your limit of integration, that's fine. It doesn't actually matter, you guys. So, but if that gives you the heebie-jeebies or you can't sleep tonight because of that, by all means, switch your A and B there. Okay, so again, I'm taking out that discontinuity. It doesn't know what to do with that because if we plug that in, I would get 0 in the denominator, which we know is not good. And then here, if you want to do a U substitution, you sure could. I think hopefully you're getting to the point where maybe you don't have to do a U substitution. You can see that, if you did do a U substitution, then you're going to get, if you let u equal x minus 1, do you see how du is just dx, right? So we're not going to have anything that's off. We're not going to be off by any kind of constant. So I'm just going to go ahead and I'm going to do my power rules. So if I add 1 to a negative 2/3, then I get 1/3. Okay, so this is going to be x minus 1 to the 1/3. And then if I divide by 1/3, that gives me 3. That's pretty nice. 0 to a. And then here we'll get the same thing. Limit as b approaches 1 from the right, and we'll just get, same antiderivative. I don't need to do a u substitution. X minus 1 to the 1/3 from b to 3. All right, and we're ready to go. So let's see what happens here. So I'm going to get the limit then as a approaches 1 from the left. Let's plug in a. So I'm going to get 3a minus 1 to the 1/3, right? Minus, now if I plug in 0, 3 times negative 1 to the 1/3. Okay, again, look at, I'm being very careful with my minus signs, making sure that I'm keeping track of everything so I don't make a mistake with that. Limit as b approaches 1. Let's put in 3 times 3 minus 1 to the 1/3 minus 3 times b minus 1 to the 1/3. Okay, good. All right, so what do we get here? So what's happening to this guy as a approaches 1 from the left? As I approach 1 from the left, I'm taking numbers that are smaller than 1. So I'm going to get a negative, but that's okay because I can cube root a negative, but it is going to go to 0, right? What's happening to this guy as a approaches 1? It doesn't care. There are no a's, so it doesn't matter, right? So what's negative 1 to the 1/3? That's a negative 1 times a negative 3, so this is 3 because this whole thing's going to 0, okay? What's happening over here? This is just going to 3 times 2 to the 1/3, right? Or 3 cube root of 2. What's happening here is b goes to 1. We're approaching 1 from the right, so this guy's approaching 0 from the right, or it's positive, but it's still going to 0, so that guy's going to 0. So what do we get here? We get 3, and then we're going to get plus 3 times the cube root of 2. And we are done. That's it. So it converges, right? It actually does work, right? We get close enough to that it works. That may not always be the case, you guys. That maybe, if we had done this same thing and we had maybe 0 to 3, and I had 1 over x minus 1 to the 4/3 dx. What happens there is when you take its antiderivative, you have x minus 1 to the negative 4/3. So when you take its antiderivative, you add 1, and that's going to give you a negative 1/3 and divide by it. But then when you put in your a's and your b's and you let a and b go to 1 or from the left or from the right, this guy's not out of the denominator anymore, so it's actually undefined. So it's going to go to infinity, and you're going to diverge. So it doesn't always converge. Sorry, I guess I did 3 examples where they do always converge, but that does not constitute all of the possible examples that we have. But again, please, please, please be mindful of good notation. Notice how I carried my limit signs all the way through until I actually took the limit. And once I got there and took the limit, I didn't need my limit signs anymore. Please watch notation. I'm going to be very picky on this next exam with notation, and let me know if you have any questions.